Okay, so here we are. We'll learn statistics. Okay, so why do we study statistics? All right. All right. So this is so statistics. Well, we study anything. I argue that the reason why we go to school and study any subject is to better understand the world around us. Okay, and statistics helps us to understand the world around us by helping us understand variation. Okay, so let me write this. Okay, statistics. All right. Study I really like this chalkboard here. Okay, and so statistics. Understand the nature of variation, and that in turn allows us to draw conclusions about the world. Limited data. All right. So as you do your homework this week, which involves reading Chapter 1 and Chapter 2, the beginning of Chapter 1 just talks about a bunch of examples or statistical kind of some studies where statistics can be applied. And so we will, so I will just bring one up here. And here's the example. Okay, so in this study, they took a bunch of rats, okay, and they wanted to see, or I'm sorry, not rats, mice, and they took some mice and they wanted to know if exposing the mice to E. coli or keeping them in a germ-free environment had anything to do with the development of liver tumors. Okay. So is there an association between the environment and the development of liver tumors? Liver tumors in mice. Okay, so here we are, and so we had a total of 62 mice.
What page is that?
This is on page 2. Okay, table 112. All right. 62 mice, and we put them into 2 groups. All right. And so some of the mice we exposed to E. coli, and the other mice we kept in a germ-free environment. 13 of the mice. 13 of the mice were in the E. coli group, and 49 mice were kept in our germ-free environment. Alright? And some of the mice developed liver tumors, so this was the result. So, well, the mice didn't have very nice lives. They were either exposed to E. coli or kept in germ-free environments. And then at the end of the study, they killed them all, and they opened them up and they said, "Are there any liver tumors?" Okay, so I mean, it wasn't. Okay, but some had liver tumors and others did not. Okay, so in those in the germ-free environment, 19 developed liver tumors, where 30 did not. And those that were in the E. coli environment, 8 of them developed liver tumors, and 5 did not. Okay. So what was the rate of liver tumor development in the two groups?
Is this a percentage or a ratio, or what is that?
Yeah, you can, we can do a percentage or proportion, it doesn't matter. Okay. Yeah, ratio is the same thing as a proportion anyway. Well, it's all different words for the same idea. Alright, so for those in the E. coli environment, 8 out of 13 developed liver tumors, right? So for E. coli, 8 out of 13 developed liver tumors. So what is that? That's like 60 something percent. 62%. Okay, 62% developed liver tumors. Alright, those in the germ-free environment, 19 out of 49 developed liver tumors, and so that is what? 39%. Alright. So, based on what we see here, what would we say? There's an association between the environment and the development of liver tumors in mice. Yes, no? And what seems to be going on? It seems that exposure to E. coli increases the rate or risk of liver tumors. Would we kind of agree with that or something? It appears that way, right? Okay, so it appears, so we say 62% is bigger than 39%.
Is the assumption that all of the conditions are the same?
Huh?
I said, is the assumption though like that all the conditions are the same?
Oh, conditions, what do you mean by
Other
conditions?
than E. coli and germ-free.
Yeah, so if you're gonna do a study, okay, you wanna keep, you want everything about, so we'll talk about a proper experiment here, okay? In a proper experiment, we keep everything about these mice as identical as possible, with the exception that some are exposed to E. coli and others are kept in a germ-free environment. We want to keep the food that they're eating the same. We want the everything else, the temperature, the I don't know,
The amount of mice.
the amount of mice.
This is 13.
Yeah. So maybe they're isolated in one box at a time or something. Who knows? Okay. We want everything about the two groups to be as identical as possible, with the exception that one group was exposed to E. coli and the other was kept in a germ-free environment, so that if we see any difference, we can trace the cause behind that difference to just this, what we call the treatment. Okay? If we did not do that, right? Let's say we gave the E. coli mice all like I don't know, we gave them beer and alcohol, and the other ones we didn't, okay, and then they developed liver problems, we wouldn't know, is it because of the E. coli or is it because of the alcohol, right? So we don't want to do that in an experiment, okay? And you have, and there's a whole field dedicated to experimental design, and we're going to talk about that in like week 9 or something for like 20 minutes. But okay, so anyway, but just this is before we get into all of that, just a taste or a perspective is that it appears, I'm going to write this, it appears that exposure to E. coli increases the risk or rate of liver tumor development. Okay, and basically we're just saying 62% is greater than 39%. Okay. That's what we might say. However, after we approach, learn a little bit more about statistics, okay? And in the beginning, we're gonna have to talk about just like data and probability, and it's not as exciting. But then later on, we get into the statistics, and it's more fun. Is that when we learn about this, we're gonna see that, you know, there's this idea of just natural variation, okay? And we could say that E. coli and this germ-free environment actually have nothing to do with the development of liver tumors, okay? That keeping mice in an E. coli environment or keeping mice in a germ-free environment, it actually has nothing to do with developing liver tumors. Some mice are going to develop liver tumors no matter what, okay? And other mice will not. And whether we put them in an E. coli environment or a germ-free environment, it has nothing to do with whether or not they develop liver tumors. Some mice are just going to develop liver tumors. Okay. So this is one. After we learn statistics, we're gonna kind of get this approach in our mind. Okay. So some mice develop tumors anyway. Okay. So overall, how many mice developed liver tumors? 27 developed liver tumors, right? And 35 did not. Okay. So we could imagine, okay, let's just say at the beginning of the experiment, let's say we could freeze time and enter a parallel universe, okay? And let's say somehow we knew that 27, okay, so let's say, you know, we entered a parallel universe, we got 62 mice again, and we know already that 27 of these mice are going to develop liver tumors and 35 will not, okay? Now I could just mix up the mice and put them into two groups, okay? And in one group I put 49 mice, and the other group I put in 13 mice, okay? And I just mixed them up, okay? And I just assigned them to two groups, and I'm gonna raise them in identical conditions. So both of these things are absolutely identical, okay? And what? At the end of that study, some mice will have liver tumors and some will not, right? Okay? A total of 27 mice will have liver tumors and a total of 35 will not. And we know that because I just randomly assigned them to two groups, one was with 13 mice and the other with 49 mice, we know that there's no reason why one group should have a higher or lower risk rate of liver tumors than the other, okay? Because we raised them up in identical environments, and it was just at the beginning I put 13 in this group and 49 in the other, but some mice, and we know that the mice are going to develop liver tumors anyway. Okay, does that make sense? Okay, but because of that random assignment, is it possible for 8 mice out of 13 to develop liver tumors just from random assignment? Okay, just because I mixed them up and I threw them over here, is it possible that 8 of these 27 liver tumor mice end up in this group of 13? Yeah, it's possible, okay? Is it possible that 9 out of the 13 mice end up with liver tumors just from random assignment? Sure, that's also possible. Is it possible that all 13 mice end up developing liver tumors just from random assignment? It's possible. It's probably not very likely to happen, okay, but it's possible, okay? And so we're going to learn probability to kind of understand what is likely and unlikely to occur, okay? And so, you know, if we did the study where all 13 ended up with E. coli, and I mean, all 13 mice in the E. coli group ended up with liver tumors, we would be like certainly convinced that that E. coli has something to do with liver tumors. But it's also possible that it actually has nothing to do with it, and just somehow, because of the random assignment that was done at the beginning, a bunch of mice that were going to develop liver tumors anyway ended up in the E. coli. Okay, so anyway, if we do the probability, okay, and in this case, we would either do a chi-squared test, okay, we'll learn about this later, or a Fisher's exact test. Okay, we can calculate what's the probability that just from random assignment, 8 of these mice, 8 of the mice that were going to develop liver tumors anyway, ended up in this group of 13. Okay, and it turns out that that's going to happen 12% of the time. Okay, so we could arrive at these results simply by random chance. 12% of the time. Does that sentence make sense? Okay. So again, the idea here is that we're in a parallel universe. We're saying 27 out of 62 mice are going to develop liver tumors anyway. I'm just going to mix up these rats, and I'm going to create one group of 13 and a group of 49. And just from random chance, there's a 12% chance that 8 of the mice that are going to develop liver tumors end up in that group of 13. Okay. So, now that I've given you this bit of information, how do we feel about this original statement? The answer to this original statement. Is there an association between the environment and the development of liver tumors in mice? Possibly.
Depends.
Depends, maybe.
We can't know.
Yeah, okay. So, and you're going to find out that this is what we say a lot in statistics. The answer is maybe, okay? Possibly, all right? So is there an association between the environment and the development of liver tumors in mice? Okay, we've done this, and we see 62% of those in the E. coli group develop liver tumors, and 39% in the germ-free environment develop liver tumors. So it seems, so the answer is possibly, and this is what our data shows. However, it's not equally possible, but there is a probability that we cannot ignore, a 12% probability, which I can't just ignore, that this result we see here is just a result of random chance. Okay? So because things in life are not completely under our control, different things happen. And there is a very real possibility that I cannot ignore that these results happen from random chance alone. Okay? And so our answer is, well, with this much data, I cannot make a strong conclusion. And that's gonna be, that's all we can say at this point. You just say, I don't have enough data to decisively conclude that there's an association between liver tumors and E. coli. So I'll write that down because that's worth. So now that we know this, we can say, I do not have enough evidence to conclude that there is an association between E. coli and liver tumor. Okay. All right. So there's a. We will eventually get to this. Okay. Or get to studies like this. This is chapter 9, I would say, 9 or 10. So I think that's like week 8. So we'll get there, but it takes a little while to get there. Okay. We first have to just talk about how do we describe data in the first place and learn a little bit about probability. And there's other stuff that we do first. Okay. But we'll learn how to come to this 12% number. And this is kind of a taste or preview of what we'll be doing in statistics. Okay. So does that seem good? Seems interesting. Okay. Because as a kid, and this is when I say statistics changed my life, is that as a kid, you do a science fair or something, and maybe you get some numbers like this, and you'd say, oh, 8 out of 13, 62%, 19 out of 49, 39%, 62 is bigger than 39, therefore it means this, right? But then there were always times where it's like 53% versus 51%, or something, and you're like, oh, does that mean this? Maybe, maybe not, okay? And statistics kind of opened the idea that, oh yeah, you know what? There is a difference, but maybe it's not that big of a deal. Okay. So anyway, you read the rest of chapter 1, and it talks about just some more other things that we can do in statistics. And then there's just a few other topics that I need to cover from chapter 1. Okay. Okay, so we obtain data. So just a very brief talk about obtaining data. And we obtain data either through observational studies or experiments. And there's a lot that we can talk about. But the idea behind an observational study is that we just observe, okay? So in an observational study, we observe our subjects. We do our best not to interfere with still, you know, just the fact that you are observing might introduce what we call a panel effect, which just means when people know that they're being watched, their behavior changes, okay? But we do our best to not interfere with their lives and the choices they make, okay? So, you know, it still might have a panel effect. Might still have might, no. Still possibility. Okay. But ideally, we just say, you know, thanks for signing up for this study. We're just going to watch what you do. Okay. Go on with your lives and check in with us, and we'll take these measurements on you. Okay. Or you might, with an observational study, you might just go through historical data. Okay. So there's prospective versus historical studies. Okay. So prospective means you come up with the idea and then you go out and study. Okay. So you gather the data. Gather data yourself.
So wait, that means there's no experiment involved, or?
Yeah, there's still no experiment here. Right? These are observational study. So a prospective observational study is something like, we want to, I don't know, learn about brain chemistry or something, okay? And then you say, we need volunteers, and we're going to ask you some questions, and take some measurements about you, okay? And then you say, okay. And maybe you get, you know, you can see, do men have this and women have that, or whatever, okay? So you gather the data. There's no experiment being done there. You're just gathering data. Okay. In historical, you're just somebody else has gathered data, and you're just going using their data. Okay. Using someone else's data. All right. But the thing about observational studies is that you can never draw a cause and effect conclusion. Forgot to charge my second battery. Let me get this set here. Sorry, charged. Okay, so. Okay, so you can never draw a cause and effect conclusion from an observational study. Is there a reason why? Never draw cause and effect conclusions. Okay, well the reason, or what's that? Yeah, well, yeah, there's something called a confounding variable. Confounding variable or lurking variable, okay? They're different things. But lurking variables, basically, if we did an observational study and we just went around to different places of the world and we looked at, let's say, infant mortality and literacy, okay, we would find out we would see an association between those two variables. Okay, we would find that in places with low literacy, there is higher infant mortality, and in places with high literacy, there is lower infant mortality. If we just went around the world and we looked at different places and stuff like that. So, does that mean if we want to help save babies' lives that we just have to get people to read more?
Could be.
Maybe, right? But no, that's not. It's not a direct cause and effect thing. It's not that reading causes babies to somehow live longer, or not live longer, but not die. Exactly. Okay, so reading doesn't somehow help babies not die, but there's lurking variables. Okay, there's other things like just the economic development of the country. Okay, which plays into a lot of things, right? Generally, countries or places that have higher economic development have higher literacy rates. They also have better healthcare systems, so lower infant mortality, things like that. Okay, so there's other things that go on, and so just because you see two things happening together doesn't mean one causes the other. Okay, there could definitely be a cause and effect relationship. However, you cannot just from observation alone say this definitely causes the other thing. Okay, so you can never draw a cause and effect conclusion. So they will say the other thing is that correlation does not equal causation. That's kind of this thing, although correlation is a specific application of okay. So anyway, that's observational studies. Let's talk about experiments. So with experiments, you find volunteers, or you find people to study, and unlike the observational study, so in observational studies we observe our subjects. In experiments, we do as much as we can to control a lot of things about our experiment, about our subjects. Okay, so we control as many aspects of variation as possible. Basically, let's say you want to know what could have an impact on blood pressure. Okay, so you want to know, maybe you're developing this blood pressure medicine, okay? And so you want to know what could have an impact on blood pressure. Well, ideally, you could find a bunch of subjects and you could control all aspects of their life so that the only difference between this group and this group is that one group has blood pressure medication and the other group doesn't. Okay, you want to be able to say both groups have the equal amount of stress, both groups have the same diet, both groups have the same exercise regimen, things like this. Okay, obviously we can't practically do that, but if we could, we would. Okay, if there were no ethical constraints on experiments, okay, we would do as much as we can to control as many aspects of variation as possible. Okay. Yeah, so a lot of data was obtained via unethical means back in the day, but today we say that's not right. So anyway, we would, in an experiment, we control as many aspects of variation as possible, with the exception, okay, control as many aspects of variation as possible so that the subjects are exposed to nearly identical environments or whatever that might be, okay? Etc. Okay, environments, etc. Okay, with the exception of the treatment variable. Okay, so we only want the treatment variable to be the thing that's different between our groups of subjects. Okay, so ideally only the treatment is the thing that differs. Okay. And then if your data support, so if the data from the experiment support it, you may make a cause and effect conclusion. So in experiments, you know, we use placebos because if we're going to give people drugs, we also know that there's this placebo effect where people who, whenever they receive something, there's this psychological thing that somehow affects things. We don't fully understand how it works, but it does. And so we give them placebos as well to try to differentiate between what's the result of the placebo effect versus the actual drug. Okay. That's part of controlling as many aspects of variation as possible. Because we also want to control that placebo effect impact. And then in your reading, it'll talk about blinding and double blinding, which is all just about, it's all part of controlling variation. Okay. As we, okay, so that's observational studies and experiments. Does anyone have anything to add to that or say anything? Yeah.
Remember when you got your 12%?
Uh-huh.
You said you can use the Fisher example last year. Would both those different methods give you the same 12% then?
No. I think the 12% probably came from a Fisher exact test, right? For large samples, they give you very similar numbers. But it's beside the point, but the small sample will be different. Okay.
I do have a question.
Yes.
So, seems like we're favoring experiments over observation, right? Does that mean in the world of statistics, observation has no room, or is no interest?
Definitely, observational studies are valuable and useful. Okay, and many times experiments just are not possible. Okay, because of ethical or practical constraints. Right, like if we wanted to know, does the use of cocaine have an effect on brain chemistry? We can't just get volunteers and say, guess what, tomorrow you guys are going to start using cocaine, and we're going to study what effect it has on your brain, okay? We can't do that. We can't do that. So, we can do that to mice. um, but anyway, well, maybe that's not right. But so yeah, so experiments allow us to draw cause and effect conclusions. Observational studies we can't, but it gives us an idea of things that could be related. Okay, so even if you cannot say this definitely causes this, you can say there's at least some kind of connection. Maybe it's not the cause and effect connection, but there's some kind of connection between these two things. Okay? And that's still very useful, and a lot of times we have to do observational studies because experiments aren't possible. Yes?
Sometimes, like, maybe companies lead towards observational studies because they can lead to bogus conclusions.
Perhaps in
Like, I'm thinking like pharmaceutical companies or weight loss companies.
That's based on assumption that they are unethical to begin with. So that's a bit.
Yeah. I mean, things. If you are unethical with any set of tools, you can do something unethical.
I
And
guess
so.
I guess I'm kind of just wondering if it's less, because you're saying it's less conclusive than an experiment, right?
Okay. The conclusions that you draw from an observational study cannot be cause and effect or causal in nature. That's all I'm saying. So, you can still make conclusions about association. You can say there's some kind of connection here, but you cannot say this is the reason for it. Okay. That's all. Okay. I mean, a lot of a lot of studies are observational in nature, and that's okay. All right, they're still valuable, and maybe at the end of the day, all we can say is that there's some kind of association here. It may or may not be cause and effect related, but even that information is useful. Okay. But yeah, there's always basically. Every time they say this and this might cause cancer, okay, it's because there's some kind of, it's probably from an observational study, right? Because you can't just say, all right, does UV rays cause cancer? Guess what? We're gonna stick you under UV rays and we're gonna keep you in the dark and we're gonna see what happens to your body. Okay, we can't do that, right? But we can observe a bunch of people and we can say, definitely all these people who are exposed to the sun for long amounts of time, their rate of skin cancer was a lot higher than these people. So we think there's a connection there, okay? And there might be a lot of evidence that says there's probably some kind of connection here, okay? But to conclusively say this is the cause and this is exactly going on, that's a lot more difficult, okay? You might have to look into the so statistics just kind of says there might be a connection here, and then science or whoever, other people might actually look at, the mechanisms behind what's going on here. Okay, and so a lot of times people find the mechanism, and then the statistics will support that. And even though it's an observational study, we can come to some kind of good conclusion here. Okay, but yeah, ideally we could just do experiments, and we could say, oh yeah, we got a bunch of people, and these people we stuck under the sun, and these people we kept in a dark room, and this is what happened, okay? And stuff like that. and you can have stronger conclusions, but of course that would be unethical. So you can't do that. So experiments have their place, observational studies have their place. It's okay. All right, let's talk. This is moving on to section 1.3, and this is just about. It's kind of the idea of drawing conclusions about the world from limited data, right? So I talked about this idea is we want to draw conclusions about the world from And so the idea here is that we cannot study everyone in the world, or everyone that we're even interested in. Okay? And so I write the world in quotes here because this just represents everything that you're interested in. Okay, so the technical term, or the term we use, is the population. The population is the group that represents that has everyone that you are interested in. Okay. So perhaps if you're doing some studies on prostate health, your population would probably be adult males, okay? Maybe adult American males, or whatever that might be, okay? If you're doing a study on something else, it might just be one specific demographic or whatever it might be. That is your population. You cannot study everyone in the population, okay? It is not possible or practical to study everyone in a population. So you study a group selected from the population, called a sample. Okay, and this is called a sample. Alright, so yeah, so maybe you're interested in autism or something. And so in your population in that case would be everybody who has autism. And then you cannot study everyone who